Okay, so here we are. I have my NVIDIA Nano right there, and we are going to be continuing where we left off yesterday. So let me show it again. Down here, I installed the SSD, and we are trying to be able to understand, but when we have our operating system, we have all of our files on the micro SD card. Okay, now we want to be able to go and change that over to be the SSD. But we are trying to figure out, okay, how does the actual boot system work? What are the order of operations when you turn on the power such that it actually does come alive? Because there is this thing which is, okay, there's the bootloader, there is a separate electrical component which is running some kind of code. And how do all of these things work together? How are we able to do this, and what does it actually mean to change over our system to the SSD? Because so far, what I'm hearing is that we need to keep our bootloader on the micro SD card. Then we need to move all of our files and the actual operating system onto the SSD. Okay, so that's what we're trying to figure out. That's how we're going to be investigating today. So, yesterday, what we were doing is we were talking about that, which is we're coming up here. So the power on of the system. So we're trying to understand, how does this system even come alive? How does it power on? All right, so apply power. So the PMIC, power management integrated circuit, it wakes up the CPU. Okay, so we plug power in. Where's my power? We have power, we plug it in, and from that it gets power and the CPU comes alive. Okay, so now the CPU is going to do something, right? And what happens is the CPU runs the NVIDIA signed code in the SPI flash. All right, so this SPI flash is going to be that external component which NVIDIA has code on. Okay, fine. And so now the CPU is going to run that code. And it initializes RAM. So initializing RAM, does that mean that's a very unclear statement about what initializing RAM means. Okay, let's keep going though. Secondary boot. So this is similar to BIOS, I remember. The firmware looks at the boot order. So the firmware, which firmware is it talking about? I'm guessing that it's talking about this inside the flash, right? The firmware looks at the boot order. Okay, so where is this boot order? It finds the EFI partition on my SD card. Okay, so the other thing that we were looking at is we have up here, so we have these different things here. So I did list like block storage devices, right? And we have right now our main one, which is here. Okay. And this is the micro SD card. And on this micro SD card, we have this boot EFI. So one of the things that I'm going to be trying to understand today is, how does all of this connect? All of this is on my SD card, right? So my boot is on my SD card, and my root file system is on my SD card. And then apparently this is on the actual board. It's on a separate component, not in the SD card. And by the way, here's our SSD right there that we installed. Okay. So, all right, loads the Linux kernel into RAM. UFEI, is that this thing, right? Loads the Linux kernel into RAM and says go, mounting the root. So once the kernel has loaded, right, it's in RAM, the kernel looks at its configurations and says, where is my root file? Then that's, I think, what we want to swap over. And it currently finds it in this block partition. Yeah, this one. Yep. Okay. Initialization. The first process, which is systemd, that we've met with this character before. So yeah, systemd starts up its PID 1, and it goes and like fires up all of the other processes, and it's kind of the root node. Okay, so then our Mr. Systemd starts to come alive. Okay, which launches your desktop, the SSH server, and Olama. There we go. Okay. So, next thing is mount points. In Windows, you have your C drive and your D drive, right? Okay, in Linux, we don't do that. Okay. Definition: a mount point is just a folder that acts as a gateway to a piece of hardware. So that's different than a device folder. Acts as a gateway to a piece of hardware. Okay. Imagine your SSD is a hard drive, okay, sitting on a table. Sure. To use it, you hook into an empty folder like mount SSD. Now when you put a file in that folder, it's actually traveling through the hook and landing on the SSD. Okay, why you need them? Without a mount point, the operating system knows that the device exists, but there's no way to write to it. So do we need to like set up drivers to be able to actually write to the know how to write to the device? The migration utility. I'm referring to a secondary utility. Well, okay. So we're going to be using this Jetson stats, but then it was talking about another utility. So I'm referring to a second utility. Jetson stats provides JTOP dashboard, the most reliable script for moving the OS to a community script called Jetson OTA or root on NVMe. We are going to use the very popular one by Jetson Hacks, okay? So step-by-step migration, the point of no return. Oh, that's a little bit ominous. We will download the tool that knows exactly how to handle the Jetson Orin partition logic. Partition logic, okay. So we're just going to get this from the GitHub, okay. Format the SSD. The script includes a utility, okay, to format the NVMe memory specifically for the Jetson. This will erase everything currently on the 1 terabyte SSD. That's fine because we just put it in there. We just bought it. So we're going to format this block storage device, right, as exit for, which is just a format type. And we're using the utility to do so, which we get from here on this target. So we're passing this target in as a parameter, and then it will format it. Okay. The big copy. This will copy your entire 120 gigabyte SD card. Okay. Onto the, so then we do, from that same current directory, we do another script. Okay. And it's just copy root fs file system, root file system. Okay. Now D, the handover, updating the bootloader configuration. This tells the system to use the SSD as the root file system. Setup service. Okay. Then we reset. So that's kind of the steps that we're doing, but I also definitely want to understand and kind of learn as we're doing this, right? So, okay, once you run D and reboot, your Jetson will look exactly the same, but it will be flying. Okay, you can check and then we use this command, and we should be able to see where we currently are, this one right here. So we should be able to see where our mount point for this is. Okay. So, all right. Now the thing that, so there's still, like, I get the steps, and I have no doubt that I can do steps 1, 2, 3, 4, right? But like, that's not really the question. I can do it, I can accomplish it. The question is, though, like, there are all of these very interesting concepts which are being utilized right now, which we're kind of glossing over, and I kind of want to be able to, really take this as a learning opportunity to be able to understand. So, okay, we'll download the tool, and that's fine. And I did ask follow-up questions here, right? What are sectors, all of this, bootloader paths. We might go through this, although, do we want to just start it up, right? Like, we can try, because I heard that this one is going to take a fair amount of time, so we might want to do that. And then while that is running, we might be able to go and investigate some more things. So maybe we do kind of follow on the steps 1, 2, 3, 4, do those, and then try to, while it's doing it, understand what's happening. Hopefully we don't completely break something. Hopefully. All right, so let's power it on. Yeah. This thing is going to start making a noise, I think. Every time this thing... See? Same thing when it shuts down, it goes... Tss, and, like, I never expect it, and so it's always just like, oh, okay. What just happened? Now... Alright, so we should be able to log back in here. See if we are up. Alright, I just got a light on this one, which says that probably the OS is on. Let's try it again. There we go. Here we are. Okay, so now, where do we actually want to put this? Do we want to just put it into downloads? I guess we can just do desktop, right? And okay, sure. And so now we're going to, yeah, whatever. We're gonna clone this, clone the repo down to our is it asking me a question or is it hung? Username for okay. Is it trying to get my username here? Or is it trying to get this one? Or is it trying to get, what if I just did that? Password? I have no idea. Authentication failed. Okay. So I'm just trying to clone it down. I'm not trying to actually sign in. Remote repo not found. Fail authentication. Okay, so is it like not up or something? All right, let's see if it is there. So is it like set private? Okay, well then that would be a, okay. Awesome, great. So I was hoping for GitHub. Hold on. Okay. So we have this here. And what are we looking for? Hacks Nano. Okay. And which root on NVMe? Okay. Okay. So it appears that this is no longer active. Awesome. Great. Okay, so I guess we're not going to be doing that right now. Okay. Good. So this one is no longer there. What about this one? Jetson OTA. Okay. So we'll download. So, okay, so we will not be downloading the tool. And then that means that this is no longer valid because we don't have these scripts anymore. Good. Okay. So now, darn. Okay. We are going to have to figure out another way to be able to change things over. So I asked a bunch of follow-up questions, and let's try to maybe investigate that a little bit. So think of storage devices as a massive warehouse. Okay, so that's our block storage device, right? Okay. Sectors are the smallest physical boxes in that website. Okay, so traditionally a sector is 512 bytes of data. Oh, so not partition, sector. Okay, okay. When you use a tool like DD, you aren't saying copy this file, you're saying go to box 0 and copy the bits exactly as they are in box 0 to the new warehouse. Okay. Never mind. So these are partitions right here of this storage device, and now within there it has 512 bytes. So each thing is 512 bytes. Yeah. And now in the past, like in the last video, I was talking about how I was unsuccessfully using DD when attempting to copy over an operating system. And so that's why it's mentioning DD. So when I use a tool like DD, you aren't saying copy this file. Okay. So I'm not saying it at the file level. I'm saying go to box sector 0 and copy the bits exactly and put them in sector 0 of the new website. Okay, so when I tried to do DD on my Raspberry Pi image, why did it fail? And my question is, well, I'm copying everything over, including the partition table. And so even if I go from like 16 gigabytes to 32 gigabyte storage device, well, it should still see that it is a 16 gigabyte storage device because the partition table was set up that way. But it was just completely not working at all. Okay. So it says that I'm right that the partition table is copied over. Okay, yeah, and partition table is the metadata for that. I was about to say the block storage, but it should, if it's a partition table, it should be for each partition, right? That's the way. That's what I would think. Okay. Located at the very beginning of the disk. The partition table contains a map of the disk. Okay. So saying that the disk ends at sector whatever 31 million. Okay, and now we know that sector is just like 512 bytes. Okay, so 31 million sectors, and a sector is 512 bytes. All right. But if you put it on a 32-bit disk, the operating system gets confused. The backup partition table, which lives at the very end of the disk, is now suddenly in the middle of my 32 gigabyte disk. This mismatch makes the disk appear corrupted to many bootloaders. Okay. because I can't get it at the end. Interesting. Okay. All right, so trying to formulate follow-up questions. First one is first one is pretty obvious. This repo no longer exists, period. All right, so that is the first one. Second is going to be about partitions. So I'm going to say a partition table is going to be for the entire block storage device, comma, or is it going to be for the particular partition, question mark. Now I'm going to come here, go like this, and then say, paste that into there. So how many partition tables would I have in this situation, question mark. Do I have an individual partition table for every single partition within my MMC BLK 0, comma, or is there only one partition table for that entire block storage device, question mark. Where are all of these things located, question mark. Okay. So, actually, I'm going to say, where would the partition table actually be located in all of these, question mark. Okay. Now I know that it's going to say it's at the beginning of the file, right? Or beginning. But okay, beginning of where, right? And I believe that that has some connection with the E or UE. There's so many different things going on, right? Like there's so many things. I'm trying to even understand what I don't understand. Now, those partition tables are going to be at specific memory addresses, comma, I'm guessing, comma. And is this what you are talking about with that? What did it even call it? UFI or something? Yes. EFI partition. Firmware looks at the boot order. Okay. So, all right. Now, the Raspberry Pi and the Jetson are very different boot flows. Okay, so a Raspberry or a Pi image expects the CPU to look for a specific file called boot code binary. Okay. On a FAT32 partition. Okay, so instead of like whatever exit 4, right? If your dd command didn't align the start of the partition exactly where the firmware expects, where is it going to expect? The handshake never happens and the system stays dark. dd command didn't align the start of that partition. What question am I even going to be trying to ask right now? Okay, bootloader paths. Yes, there are multiple paths because modern systems like Aura Nano have redundancy. AB slots. NVIDIA often keeps 2 copies of the bootloader. Path A on the SPI flash, that's the external one, fails to find an OS, it can jump to path B, the files. They look for bin or EFI files location. They live in those tiny partitions that we saw here, like partition 2. Okay. Through 9. Oh, okay. They are invoked by the CPU's internal read-only memory. It's hard-coded to look at specific electrical addresses on the storage bus. Okay. So that's what those things are. Partitions, block storages. I'm trying to go through partitions, block storage devices. Can we go through how all of these things are connected? Question mark. Block storage devices, comma, partition table, comma, partitions, comma, bootloader, comma. We're gonna have to figure out more things. Okay. We're gonna have to add to that list. Okay, so rsync. Rsync is a standard, extremely powerful utility. Okay, Linux utility. What it does, it is a Delta copier. It looks at the source and destination. If a file is already there, it hasn't changed it, so it skips. So this is in like contrast to DD, right? Okay, why it's better than D? Yeah. Okay, so it operates on files, not sectors. Okay, and we now know what sectors are. Okay. It ensures that file permissions, who owns that file, and symbolic links stay exactly the same. Okay. Got it. Okay, so these are the instructions for the kernel. These are, okay. Exit Linux configuration. This is an older text file located at boot in the boot directory, okay? It tells the bootloader, load the kernel from this folder and use this partition as root. Okay. Okay. Set root menu. On the Aura Nano, this is a more modern script service. It modifies the variables that the UEFI firmware reads. Okay. Another thing is boot sequence. Okay. UEFI. Okay. UUID. All right, they're connected in spirit, but both serve the goal of telling the system where this lives. Okay, so we're the UEFI. What does it even stand for? Okay, but its goal is to tell it where the root file system lives. Great. Okay. So this SPI flash code, which is on the external device, it is actual code, the hardware. The NOR flash chip is physical storage, like tiny permanent SD card soldered on the board, the logic. It's not logic gates like an FPGA, that's what I was wondering about. It's a collection of compiled C and assembly code, okay? So when I flash the Jetson, I'm using a specialized protocol over the USB-C port to write data onto that tiny chip, okay? Okay. So discovery, and this is the question when I was talking about plugging in a USB, like a USB storage device, right? And it doesn't happen at startup because this is happening whenever I plug in my device. And so there needs to be some discovery. That's the question that we were asking from yesterday. So, all right. You're 100% right. This happens via interrupts. Okay. When you plug in a USB, it completes an electrical circuit. Okay, good. The USB controller sends an interrupt, okay, signal to the CPU, says, hey, something arrived. Okay, the kernel stops what it's doing, runs a probe to see what was plugged in, and creates a new block storage device in, okay, it'll be dev for device and then SDA. Okay. So now, why do we need partitions? Think of partitions as a hard wall inside your warehouse. Okay. You can keep your operating system on one partition and your 1 terabyte AI models in another. If the OS partition gets corrupted and you have to reinstall your AI models, the models remain safe. Okay. You can set partitions to be read-only so a virus cannot delete your boot files even if it has access. Okay. So anything else you want to explain? All right. Take a sip of coffee and should I take a breath? All right. Okay, so how many questions did I ask? 3, right? And now we are... Okay, whatever. So since the old script, we're gonna go back up, but first, since the old script is here, actually recommends for the rsync method, which is much safer for understanding what's happening. Okay, so here's the new plan. Instead of a magic script from a dead repo, yeah, we will use the tools already on your system to do this manually so you can see the gears turning. Okay, so we're going to, and I just want to read this so that we have more context when we go back up and we're able to already know like what is important. Yeah. So create the partition table on the SSD. We need to give your SSD a map. Okay. This opens the disk partitioner. So fdisk, so we are doing the fdisk command, right, on this file location, which is here, this one, this block storage device, okay, inside fdisk, G to create a new GPT partition table. Okay, so now we are going, okay, see, I like this a lot better. I like this a lot better because I'm doing it myself and I know, like it's teaching me, oh, I see what a partition table is, because I am creating the partition table myself inside of this block storage device. I should say, when I say I like this method a lot better, assuming it works, right? Like, there's a lot more tendency towards error in this method because you're doing everything manually. Anyways, so now we are going to type in for a new partition. So see, here is the partition. Dust or something. Here's the partition table that we're doing on this block storage device. Then we are going to create a new partition. Oh, maybe that's it. So we're creating a new partition, and this partition table is on the entire block storage device, right? So I'm just gonna say like what I think is happening. For this entire block storage device, we're going to have a single partition table. But this partition table is going to give us information about the location of this partition, and this partition, and this partition, and this partition. I was thinking it was like, oh, for this partition, here is the file system. Like, is it FAT32 or is it exit4, or like what's going on with or how many bytes of memory is in here. This one is 128 megabytes, right? Or I thought that's what the partition table was, but if it's at the block storage device level, it can still have all that information, like, but it would also be like, oh, this partition starts at memory address, whatever, hexadecimal, blah, 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 blah. It's 117.9 gigabytes. It, major, minor, and then, like, mount, like, it's the root file system. Okay. So, press enter for all defaults. This creates one giant partition. Yeah. Okay, so W for write and exit. Okay. So now, phase number 2, the format. Creating the file system. Okay, so creating the file system. Now we organize the room we just built. So we just built a partition, okay, on the SSD. So now, make file system in the type of exit4, okay, and this target, which is, it's not here yet because we haven't done the partition yet, right? N1, right, and then P1. So we haven't done the partition. Once we partition it, we should see like kind of similar to this. So we have the block 0, but then we have this like P1. So we should see something similar to like that without the slash yet because we haven't done that. That's what we're going to be doing here, I think. So All right. We need to hook. Awesome. So now we are going to do the hook ourselves. We need to hook the SSD to a folder so we can talk to it. But this seems almost like recursive, right? Like, how do I formulate my like feeling towards this? Because I am living somewhere on the file system, right? And now I am saying I'm hooking the file system here onto myself from myself. I, I, I'm not articulating it correctly, but something feels off. Okay, we need to hook the SSD to a folder so we can talk to ourselves? So it can talk to us? Right? Like, so, okay. I don't know why I feel uncomfortable about that, but I do feel uncomfortable. We need to hook the SSD to a folder. So we are going to make this mount point, or make this directory, and then we're going to perform the command, which is mount, and we are going to provide two arguments, one of which is the path to the partition and to this file location. Okay. But then how does that change the boot sequence? All of this, right? Like there's a lot. Right. Oh, this is just phase one? Okay. No, this is phase two. Okay, so. A partition table belongs to the entire block storage device, not individual partitions. Got it. Where it lives at the very front of the physical disk. Okay, so sector 0. Now, again, okay, here we go. Now we see now I know what sector 0 is, right? A block of 512 bytes. How many do you have? You have one for the SD card. Yeah. And currently 0 for the SSD until we create one. Okay, yeah, so we need to create a partition table. Okay. The structure. Think of the partition table as contents at the beginning of a book. It says chapter 1 starts at page 100 and ends at page 500. The chapters themselves don't have their own tables. They just contain the data. Okay, so the EFI connection. You guessed correctly. The partition table tells the system where the EFI partition is. The EFI partition is just a normal partition formatted in a way that the bootloader can read. So that implies that different partitions can have different formatting, right? Can you go over exactly what the different formattings actually mean? Question mark. And you said that the EFI partition is usually going to be in FAT32, comma, and so the other partitions within the exact same block storage device are going to be different file systems. comma, and this is going to be kept track of by my partition table, comma. Is that correct? Question mark. Okay. The partition table tells the system where the EFI partition is, and okay, so the bootloader is going to use that and find the executable files. Okay. So connecting the concepts, the handshake. All right, so block storage device. The physical hardware, okay, the physical building. Partition table, the map at the front desk. Okay, yeah. Partitions, the rooms, okay, inside of the block storage device. A unique social security for the partition. Okay, so this UEFI reads the partition table to find the room on the block storage device that contains the boot firmware. Which is the program which starts the operating system. Okay, I think I got that right. Let's see. So the UEFI is the code which is on the external electrical component which is flashed, comma. When power is applied, this UEFI will start looking and reading the different partition tables, and it is trying to find something which is EFI, period. Because the UEFI is going to know how to read partition tables, comma, it will find this EFI thing, period. Now the EFI is going to start, and the EFI is an executable which is called the bootloader, period. This will start running code, and it is going to look for, it's not going to look for, it is going to run, it is going to load the operating system. Okay. But I'm also confused about if the UEFI and the EFI are actually two completely different things, comma. Also, how does the UEFI read the different partition tables which are within the file system if the file system has not even been brought up yet, comma. Does it check all of the block storage devices, comma, and then the EFI bootloader is going to check for the root file system, question mark. All right, so power on, the CPU wakes up, SPI flash code. Right, the SPI flash code, that's different. Oh, man. Okay. No, UEFI initialization. The SPI flash code hands off to this. Okay. Where is it located? The discovery. This scans all block devices. It looks at the partition table of every disk it finds. Okay, that makes sense. It looks for a partition flagged as EFI system partition. Okay. UEFI looks at the internal boot order list. If the list says boot the device, okay, it searches all connected disks for that specific ID. This is why your migration will work. We copy the data, find the SSD's new UID, and tell the UEFI I'm gonna say we are using so many acronyms right now, and I think it would be very helpful if you tell me what all of these acronyms are actually meaning, period. Maybe I'm having difficulty keeping everything in my head and mixing things up, period. Okay. This is why your migration will work. We will copy the data, find the SSD's new ID, okay, looks at its internal boot order. If the list says boot the device with this ID, since the old script is gone, we will use, okay, so now we're doing something else, right? So this is the other one. So we already went through this. Maybe we will read it again, but a question that I immediately have is, under the updated migration path, comma, it seems like we are just creating a partition on that block storage device. Then we create the table, and after that we will make it into an file system type, comma, and then we do something with mounts, comma. But I don't see how this does anything to change the way in which our system actually boots up, period. I don't even see how we are transferring over any data, period. It just seems like we are formatting the block storage device at those steps, period. So we're turning it into exit 4, okay. Alright. Let me come here and do question number 5 for this. Can you tell me exactly what goes on in this step? Question mark. So what is the before and after state of my block storage device partition, and why is it necessary? Question mark. The mount. Okay. So once again, there was something that doesn't seem right about this. Not that I don't think it's right, but it just something seems off. That it's like recursive or something. I also don't quite understand what's going on here, and it also seems a little bit weird because it seems like it is almost recursive insofar as I am on my file system creating a new random directory, but then pasting or connecting this block storage device onto myself, but then supposedly this is supposed to be who I am myself, period. Or my parent, period. And what does the mount command actually do? What are the before and after states of this command? Question mark. All right, what do we think? Good? All right, let's go. All right. Okay, is it just coming up with... It's not keeping the questions like aligned anymore. Acronyms, which was like question, whatever, 3, I think. Yeah, 3. That's whatever. As long as it answers them, that's fine by me. But just an interesting observation. Okay. UEFI. Unified Extensible Firmware Interface. Okay, so it's some kind of interface. The manager. This is the code in the SPI flash. Okay, chip. Okay. Got it. And that is different than the EFI, which lives here, not on the SPI flash chip. It lives on the SD card here. Okay. So now we have the exact same thing, but without the unified. So this is Extensible Firmware Interface, EFI. Okay. The language. It's the original name for... Oh, okay. So it is the same thing? So EFI system partition. Maybe this is the system partition? The lobby. A specific partition where the manager looks... Where the manager, this one, looks for files. I want to check if my understanding is correct, comma. So the UEFI is going to be the code which is actually living inside of the SPI flash chip, comma. When it starts up, it is going to look at the EFI system partition. Now, the system partition is not living on the SPI flash chip, comma. It is actually living on my block storage device. And so this makes me think that what I'm seeing, which is /boot/EFI living on my SD card, is maybe like a map instead of actual code? Question mark. Okay, so just ID, GUID, right? Partition table. The blueprint. The modern map of the whole disk replaces master boot record, I think. Okay. And so here is the partition table. Okay. Universally unique identifier. Okay. The ID card, a long string of numbers that uniquely identifies a specific partition. Okay, so UID, its job is to identify specific partitions. There is no one there, but it's probably in one of these things. Okay. Fourth, extended file system. The storage system. The standard way Linux organizes files on a disk. Organizes files on a disk. Okay. Okay, so how unified extensible file, what was it? Unified extensible firmware interface. How unified extensible firmware interface reads the disk without an OS. So the chicken and the egg, right? So the unified extensible firmware interface code in the SPI flash has a tiny built-in driver for exactly one file system. Okay, so for one file system. This FAT32. So that's the file system which is like acceptable to the SPI flash. The process. It doesn't need Linux to mount the disk. Does not need Linux to mount the disk. Why is that important? Well, let's think. Linux, so it doesn't need the operating system to mount that actual disk, right? Which is good because the operating system has not come up yet. Okay. So one question that I asked is about mounting. And I feel like that might be where some of my confusion, or not confusion, it is a lack of knowledge, right? I don't know what mounting actually does and why it's important, why it's needed, and therefore I am confused about the boot up process. I think that that's what's going on. Okay. So it does not need Linux to mount the disk, okay, which is FAT32 type. And so the code in the SPI code is a built-in driver for exactly this particular FAT32 like type. Okay. The process. It doesn't need, yep. So it speaks this language directly. Okay. It reads the first few sectors to find the GPT, the blueprint. So it's it being the UEFI, United Extensible Firmware Interface, unified, okay, which is the SPI flash living on the external driver. It's code that can only for exactly one file system. Okay, so it can only take in FAT32, or it can only do FAT32. It doesn't need any operating system. It speaks directly the electrical language of the bus, and it will look for the first few sectors to find this GPT, something partition, global partition table, GUID partition table, okay? Once it knows where the lobby is, ESP, EFI system partition, so this is my ESP, right? And it's going to be FAT32, which is what that software can only take in, okay? It uses a tiny built-in FAT32 driver to look for files ending in EFI. Okay, I think I'm starting to kind of see what's going on. Okay. So what I think is happening, I actually might need to, I want to check my understanding. Okay, so I now have a little bit of updated understanding. So to see if this is correct. The UEFI is going to be code which I flash onto the external component, which is the SPI device living on my NVIDIA PCB board, period. This firmware does not need any operating system to run. Once power is applied, it is able to speak the language of going into each of the storage devices which it is physically connected to by wires, comma. It is going to do the job of trying to look through each of those storage devices and checking their GPT partition table, and it doesn't need any kind of drivers because it knows how to speak that language, comma. It will be checking this GPT for specifically a EFI system partition, which in my case is this /boot/EFI currently living on my MMC BLK at partition 10 on my micro SD card, comma. What will happen then is this particular partition within my micro SD card will contain a executable which is of the type .efi, and the entire partition of this ESP, which is living on my SD card at /boot/EFI, is going to be in the format of FAT32, comma. Now, the UEFI firmware is going to be able to run that EFI code. period. Something like this. Okay. All right. So here, this make file system ex4, before and after. So when you run this, right, you are initializing the partition. Initializing the partition. Before state, the partition exists on the map, the GPT, right? But it's just a raw block of empty space. If you tried to save the file there, the computer wouldn't know where to put the bits, okay? The operation. It writes a superblock, the master metadata, the inodes, okay? So an inode is the file index cards and the journal. The logbook to prevent corruption during power loss. Okay, so I have not heard of any of those things. After state. The partition is now a structured warehouse ready to accept files. However, it is still floating. It doesn't have a name in your folder tree yet. Okay. So there's definitely a lot more here that we need to kind of look at and investigate. However, it's still floating. It doesn't have a name in your folder tree yet. That makes sense because that's going to be the mounting, right? The recursive mount command. You hit a profound point. Linux is a single tree system, unlike Windows where every disk is a new letter. Linux insists that everything starts at root. So before mount, you have a directory. Okay. Yes, just a random directory. It is an empty folder on my SD card. Yes, correct. On my SD card, not my SSD. Mount command. You are telling the kernel, hey, from now on, whenever I go to this folder, don't show me the SD card. Instead, divert my request to the SSD card. Interesting. Okay. So it is a kernel. It is like a command to actually move over. I think I'm starting to understand a little bit more of what that's doing. So now I'm not even on my SD card anymore. I'm on my SSD. After mount, the folder here is now a portal. Okay, physically the folder is on the SD card, but logically its contents are on the SSD. Okay. Why it's not recursive? Because you aren't mounting the SSD onto itself, you're mounting the new device onto the current device. Okay, I think I'm seeing it, but now, okay. Okay, so I now on my SD card, I have this folder. Okay, so let me come here. So after the mount command, I have a folder which is on my SD card, and this folder will have all of the contents which I am now going to want to put onto. No, that's not right. So now this folder is one of the ways that we are able to have the SD card capture the contents within the SSD card, period. I'm guessing that what we are now going to need to do is to try to move my entire file system, which is currently on my SD card at partition number 1, and move all of that over to my SD card, comma. So we are going to need to move that over into that specific mounted directory, period. But then we are also going to need to change where we are looking for a boot file system. So whoever is in charge of finding the root file system is going to need to know where to look, period. Is this kind of correct? Question mark. Okay. Well, why the updated path hasn't moved yet? So you're absolutely right. The steps I gave you, partition, format, and mount, are only prepared the destination. Yes. Okay. Good. They didn't move a single bit of data yet. Yes. Correct. So, the missing step in the grand transfer. Once the SSD is mounted at this location, we run a command to copy the life of everything on the NVIDIA over. So now we're using that rsync, and now from my understanding, or the way that I'm looking at this is similar to DD, but it's much better that it's not sector for sector. Now we're doing file by file, okay? And we're going to obviously need to investigate every single command that's here. Sudo, we know what that does. Rsync, we're going to go and investigate that a little bit more. AEX Hawk, no idea what that means. We need to find that out. Numeric IDs, no idea. Info equals progress 2. I'm guessing that this is just like a logging thing while it's doing it. That's fine, whatever. Okay. Obviously, I know that this is our portal, okay? Does this mean like the current location, or are we saying that this is the file system? Like, okay. So it copies every file from here. Every file, okay, so this is target destination. Okay, so every file from this to this location. Okay. Why it works. It's like moving into a new house. You build the shelves, partition. Okay. You label the bins format. You open the front door, and then you move the furniture. Rsync. Okay. Now, the system still boots from the SD card. EFI, extensible firmware interface, but partition, so it means here first. But we will change one file on the SSD. Okay. Maybe 3. So can you show me kind of what the general steps are going to be for the UEFI code, comma, and then show me what the steps for the /boot/EFI.EFI code is going to be, question mark. Don't give me the actual code, comma, but give me the high level step 1, 2, 3, 4, etc. of each of those separate code, period. I think that this will help me understand the differences in responsibilities of both of these separate softwares and how they are operating and with whom they are operating with, period. Okay. I like that. I like it. Because I think I'm really murky on these two things, the UEFI and the EFI. They're interacting with each other. They're on different physical devices. One is a SPI, one is on my physical micro SD card in a side of a partition on it. They're supposedly both have code on them, and they seem to be both like searching for partition tables to be able to find the files, the root file system. So, like, I want to. Okay, let's separate who's doing what. Okay, who's doing what? How are they finding? Who are they talking to each other? I think that's going to clear a lot of things up. All right. So, by the way, I also like how we haven't like even done a single command yet. But actually, this is the way that I really like to work is first, I don't, I feel like there's a different people have different ways that they do development. I see a lot of people that they go in and they try one thing and then try another thing and then try another thing and then try another thing, and then finally the seventh time that they do something it works and great, okay, then they move on to the next thing. Me, I really do not like developing in that way because for two reasons. Number one is in terms of personal growth as an engineer. When I develop that way, I try one thing, another, and then I get something, and then I move on. What did I learn? Almost nothing. I was wrong. I said almost nothing. I will make it stronger. I learned nothing. I absorbed nothing. I got nothing out of it. It works. I don't know why it works. I don't know what I was doing was incorrect, what was correct. And then the next time that I have to do it, I'm going to have to try every single step again and run into problem after problem after problem after problem, right? Because I didn't understand what I was actually doing. I was just trying random things, changing different, you have your combinations, right? Trying different combinations until something worked. I didn't know why it works. And I can't even be, that's the other thing, is like, I can't even be sure that it legitimately does work. I think it's working. I can observe it and like it's doing what I'm hoping. But you also feel very unsettled that you're like, I don't know. I think it's working. But I can't guarantee it because I didn't know. I have no idea, right? So you don't learn much. You have no idea how to replicate it. So the next time your manager comes to you and says, hey, we need you to tweak even one thing, well, all of a sudden you have to do the entire 2 days worth of trying one configuration, then trying another configuration, then trying a third configuration. Even though it might be one little small change, it breaks everything because you don't know what's going on. It's number two. Number three is you have that unsettled feeling that like, I don't know if it's working or not. I mean, I can observe it, but I don't feel confident in it because I don't know it. And then number four is I actually don't even think it saves any time to be like, I have to solve this right now. I have to get, right? Because, as I just mentioned, you're going to be trying every single combination. And that's not an efficient way of doing things. The way that I like to do things is spend the time up front to understand every single concept that you're working with. Then, once you understand the concepts, you can start to piece things together, and you don't need to guess, like, oh, which combination do I need? Because you just know you do this piece, then this piece, then this piece, because that's obvious, right? It's obvious to you at that point. And then in a month, your manager comes up to you and it's like, hey, can we change this one little thing? You're like, yeah, sure, no problem. 5 minutes later, you got it. because you understand and you know how to change the combinations without breaking things. And number three, you feel a lot more confident. Like, yeah, of course it's working because like it's deterministic at that point. Number four is you learned a lot. Like you grew as an engineer. So it's like I was kind of making a joke like we haven't done anything yet. But actually this is in my opinion the most efficient way to use your time. Okay. Enough talking. Let's keep learning. But I do want to take a sip of coffee. I always whenever I'm doing these YouTube videos, I just like talking constantly for like a long duration of time is like your throat gets super dry. That's why I have 1 cup of coffee, 2 cups of coffee, plus I have my water right here just because like when I'm making these videos my throat gets really like Okay. The other thing that I noticed is this is completely off topic, but the other thing that I noticed is like sometimes when I'm doing my YouTube videos, I will get very like lightheaded, and I think it's because I am like constantly talking. And so that's why sometimes when I'm making my videos, I'll be like, "Hold on a second. Let me take a breath, right?" And then I'll kind of go like that, and it's because I like you don't get much oxygen, I feel like, when you're just constantly talking. And so I'll notice that, oh, I'm feeling a little lightheaded. Anyways. And by the way, yes, I just. Okay. Anyways. Yeah, that was part of it. Um, so let's get back to learning. Let's not get off track. So, why it's working. Moving things over. Okay, so how does the system switch? The magic step. Okay, so the system still boots from the SD card. Yes, so the system still boots from the SD card, okay? Now, what is it booting? It is booting the EFI partition, which should be this, right? At first, right? Which is, so the SPI code has the UEFI code on it, which will look for the storage devices, which finds this partition and runs an executable on this partition, which is this right here. But now we will change one file on the SSD called boot exit Linux exit configuration. Okay, not on the SD card. That's interesting. So we will change the line root. Okay, within this configuration, we change it to root is equal to dev. So instead of saying that our root is this SD card partition 1, which is this one right here, we are saying that it is equal to something here. We're going to have to discover what that is, but okay. When the kernel starts, it reads that line, says, okay, I started on the SD card, but I'm going to, when the kernel starts, it looks at the line, but it looks at the line on the SSD card, right? This is on the SSD card. This seems a little bit interesting because you change the line of code specifically inside of the SSD file, which if the system is booting from the SD card and I leave everything the same on my SD card, but now there is the only difference as a portal which goes to my SSD, comma, why would my EFI not go and still find the same location on partition 1 of my SD card as the root? Question mark. Why would it randomly go into a random portal, check if that portal has a, let me type that out, extlinux file, and then read that file, find that specific line of code, and then use that to boot? Question mark. Maybe I'm not seeing the order of operations correct. Period. The other thing is, doesn't this pose a security risk? Because suppose I have a USB storage device, and on this USB storage device, I decide that I am going to write a file and edit myself as the USB device to be the root file system, comma. So I, as the USB, am able to give myself permission to take over the entire Linux system, period. So imagine the situation where I am a nefarious actor and I decide to write myself as the file system. Then the system looks at me when I am accidentally plugged in by a user who doesn't realize that I am a nefarious actor, comma, then I boot from myself because the system's EFI is looking into my portal, sees that I changed something on myself as the master partition, not partition table, master, or as the root file system. Okay, and then now I have complete control to be able to do whatever I want, such as exploit the user in any way I see fit, period. So, okay. All right. Now, so that's one thing. Mounting, okay. GPT. Okay, let's press enter, see what it says, and we will be able to go here. So, time for a breathing break. All right, so isn't just a possibility, it is exactly why secure boot was invented. Okay, interesting. So let's discuss the handoff. So, okay, so interesting. The boot software handshake. So I am correct. UEFI manager is the hardware level code. The EFI executable, the OS loader, okay, is the bridge. So these are two separate things. Let's separate them. Awesome. So Unified Extensible Firmware Interface. This is the hardware level code living in the SPI. Okay, what are its steps? Number one, hardware initialization. So this code checks the CPU. So it goes and checks, initializes RAM. Okay. So I think in this situation, it just means brings RAM alive. Starts RAM up. Okay. And powers up the PCIe, USB, and SD controllers. Okay, so all of this is, as it mentioned, hardware initialization. So it, meaning the UEFI, knows how to bring up hardware devices. So, number one, it's actually interesting that you are talking about how the UEFI is able to bring up all of these different hardware devices, such as the CPU, the RAM, the PCIe, USB, SD controllers, etc., period. Is this the case that the UEFI code knows how to talk with all of those hardware devices even without a driver? So for example, if I have one RAM stick, this code will know how to talk to that RAM stick. But what if I change my RAM out for a different brand? How does it still know how to talk to that? And when you talk about PCIe, USB, and SD controllers, what actually are those? And where do they live? Okay. All right, so it brings it up. Let's just say brings it up. All right, so discovery. So it, meaning the UEFI, which is on the SPI device, pulls every physical bus. Okay, it has buses, it's connected through bus, yeah. It identifies, I have a block device on SD. Okay, so now, so this is kind of important, right? All right. So it's connected through hardware, through physical wires. And now it goes out and says, "Hey, look at this! I found a block device on SD." Okay. And I found another device on NVMe. Okay, so the UFEI, living in the SPI, checks what it's connected to, and it finds all of the physical block devices. Okay. Now, what it does, it looks at the general partition table. Was that no the GUID partition table? Okay. Of each device, of each block device, like the SD card and the SSD card. Okay. To find any partition. So it's checking the partitions, right? Like here, ding, 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 ding. All 15 partitions, okay? And it's checking for any partition that contains the EFI system partition, which lives right here, okay? And each partition has a GUID, which this GUID Kind of identifies it. Okay. Now, so it checked it. It found this, right? It found, hey, I found one. Okay. Boot order. It checks its internal boot order variable. So inside of the SPI code, it has a list of like what order gets precedent. So for example, if the order is number 1 SD, number 2 NVMe. Okay, so based off of the block storage device, it is going to look for what it should boot up. So let's say that we have a partition here. A what? An EFI partition inside of our SD card. Let's say we also have, let's imagine that there's this one right here, right? And it has partition 1 and it has partition 2. And in partition 2, it has the exact same thing, boot EFI. Okay? So there's 2 boot EFIs on my NVIDIA device in 2 separate block storage devices. Okay, now my UEFI living in the SPI is going to have an order and say, hey, I found an EFI on an SD card, and I found an EFI on the SSD, and I found a EFI on a USB flash device. I found multiple ones. Well, good thing I have an order of precedent to say load, possibly in this case, load the SD card first. Okay. So it goes to the SD card first. Okay, awesome. So execution, it goes into that FAT32 partition. So it's going to come in here, and this partition here is in the format of FAT32. Okay. And now, inside of that partition, it finds EFI boot. And what is this? Arch 64 or something like that? Okay. But it's going to find some file, .efi file. Now it's going to execute it. Okay, so now I'm starting to understand things. Now it's starting to flow. So here, it looks into this partition, which is of type EFI, or FAT32. Format is FAT32, but kind of like flagged within this entire block's GPT as an EFI system partition. Okay, it is of type FAT32, and it contains an executable, a .efi executable. The UEFI finds that and runs it. Awesome. Now we get to the point where we say, all right, great. This file, the executable that lives in here, what does it do? That's our next step. Okay, that is the separate, distinctly separate code. One was in the SPI. Now we are switching over. We are executing the code which is in the SD card now. Here. Right there. Okay, so now let's discuss what that is doing. First, let's I'm gonna get some water actually. I was thinking coffee or water. Let's do some water. All right, so environment setup. So what does this do? This is going to be the OS loader. So we're going to be now trying to load the operating system, okay? So environment setup. The EFI code starts running. Awesome. It has a limited view of the world, okay? It only knows what UEFI told it from the SPI. What does it say? Or what is it told? I'm not sure yet. Configuration check. It looks for a configuration file like this exit Linux configuration or grub. Okay. By the way, so I remember going in and trying to change my grub loader, and so I I had a little bit of like experience with this, but at that time I was very much doing the old method which I described, which was try one thing, then try another, then try another, then try another, and then eventually get it. But what did you learn? Nothing, right? So now, okay, I've seen this character before, but I didn't understand it at the time, right? Now we're getting a better context. Okay, so it's going to look for this, which we're going to need to edit, right? Or a grub configuration. So where does it look? Why does it look? And as I asked in the question like down here, right? Why would it look at a random portal inside of its file system to find something here to find this file, right? That doesn't make much sense. But okay, whatever. It's looking for this file, sure. Now I know who's looking for what file. See, now I'm trying to separate and understand how all of these characters are actually interacting. Then we can dig into how. Once we understand what's trying to accomplish what, then we can figure out how it's accomplishing it. But right now we're trying to understand just the who and the what. All right, so the pivot instruction. So it reads the line that says whatever this the root is this UID. So this unique identifier here, which the unique identifier was of a partition, correct? So let me look up here because we actually have that here. Universally unique identifier is the ID card. So what does it identify? It is a string of numbers that uniquely identifies a specific partition. So it is a number that, so it's looking, all right? So it is looking for we're saying, hey, this, so the executable goes and it looks for the configuration file. It finds the configuration file, then it looks in that configuration file to find something that says root equals to something, okay? Now, we could have root is equal to a like UID, unique identifier, and then give the partition table identifier and say this is the partition that you are looking for, which is root, okay? Or we can say root is equal to the path, but this is the path on itself, right? So that is going to be this one right here, right? So this is kind of like relative to itself. So we're here and we look relative to ourselves and we just say like, hey, here I am, and there it is. But if we want to say like, oh, I'm actually on here, okay, then we have to say like, oh, okay, there's this particular partition ID. Here's the partition ID, which contains the root system. Okay. Now, kernel loading. So it finds the Linux kernel, the brain, and the init rd, the minimal toolbox. Okay. So another question that I'm going to have is, what are we on? So we're on number 2. When you say that the .efi executable finds the Linux kernel, comma, I'm now curious about who and where the Linux kernel actually lives, comma, because I think that the root file system is not the actual kernel, if my understanding is correct, comma, the root file system is literally just the files and documents and devices which the kernel uses and manipulates, period. So, can you discuss how the .efi loads the kernel? Question mark. Okay, that's interesting, right? Okay, sure. And then we want to say, yeah, so we're going to be investigating that in probably one of these, like 2 or 3 or whatever question we asked it. All right, this and the init.rd minimal toolbox. I don't know if that's quite important right now. Although there was one thing that had a whole bunch of like, where was it? I saw, oh right, so we're gonna have to do this. So now I do want to, I don't want to get too, there was a whole bunch of like keywords that I remember saying like, oh, I don't know anything about all of this, but I can't remember if we kind of glossed over that. Where was it? I hate losing knowledge. Um, okay. All right. Anyways, oh, wait, I need to find myself. Okay, so here, let's just say come here, number 3. We do this. So this is the syncing, or the, not syncing. Well, it is syncing, but I mean this is the file transfer. A command. Can you go over every single flag in this command and tell me how it is operating? Question mark. Also, what is the path that I should perform this command in? Question mark. Do I need to do it in my desktop folder or my root folder, or is it a location independent command? Question mark. I'm guessing it's location independent because we just have the target, or the source and the destination, right? But I just want to make sure. Okay, so the order of operation, confusion. You asked why the EFI, why would my EFI not just find the same location in the SD card? Okay. The key is that the EFI code on the SD card is just a messenger. Okay, default. Currently, the messenger's script says go to partition 1. Okay, yeah. Go to partition 1, meaning this one right here. Migration. We are going to edit the messenger's script, okay, the one on the SD card, to say, don't look here anymore, go to the device here. But I guess that was kind of my confusion because I thought that this was now going to be on, I thought that we were changing the configuration on the SSD. I'm going to move this a little bit more. Ooh, ooh. Okay. Well, that was a mistake. Where are you? Come on. So I'm going to do this so that I can kind of see both at the same, oh, come on. So I can see both at the same time. There we go. Okay. So the system still starts at the SD card's front door, but the sign on the door tells the guest to go to the house across the street. Okay. Now the nefarious actor. Your intuition about the USB drive is 100% correct. This is a major security vector called a physical access attack. The vulnerability, if your UEFI is set to boot from USB first, anyone can plug in a malicious operating system. Yeah, since the OS is now the root. It has full control over the hardware, including the RAM and any data on your other unencrypted drives. Okay, good. The defense. So this is why NVIDIA uses signed firmware. Okay. The UEFI is programmed only to run EFI files that have specific digital signature from NVIDIA or you. Okay. If a hacker plugs in a USB with a custom root system, okay, the unified extensible firmware interface will look for the signature, see that it does not match, and say access denied, I will not execute this code. Okay, so by default, it uses NVIDIA test key. In a professional production environment, you would burn your own private keys into the Jetsons fuse, so only code signed by you could start the machine. Okay, so that's an interesting topic. It's an important topic, but it is not an immediately relevant topic. So I want to investigate it, but later. And the reason that I asked the question in the first place is when I'm using AI to do these investigations, I kind of view it as like putting puzzle pieces on my worldview. I don't know anything about the topic, and I ask more and more questions to try to get a more holistic worldview of this concept. And if I notice something that I'm like, I don't quite feel that this is right, that's an avenue that I need to go down to say, like, there's probably a misconception that I have. And so that's why I asked the question, because I was like, I don't feel that this is right. But now I understand, like, okay, this is a problem, and there are mitigation tactics to solve this. So it is not a problem of like my misunderstanding. So let's kind of put it on the back burner. Let's say, okay, great. There's something called code signing. You use keys. This something that we need to investigate in the future. Might be interesting, but we don't need to investigate it right now. Okay. So, what is mount actually doing? Think of it like a cable patch. Before mount, you have a physical SSD, okay, yeah, an isolated island, and a folder here, an empty box on my SD card, yes. The command, sudo mount, and then okay, and mapping that, okay, so the device to the folder, okay. So the result, the kernel creates a logical link. It doesn't move the folder, it tells the file system, whenever Timothy tries to look inside this box, redirect his eyes to the SSD island. Okay, so now, all right. So, summary of the grand plan. Format SSD. So, create the island structure. Mount the portal so we can talk to the island, okay? Rsync, walk through the portal and copy everything from the SD card to the SSD island. Switch, edit the sign. Okay. So I'm going to do this. I'm going to ask these questions, and then pretty soon we are getting to the point where we should be able to actually do the commands to run it. Okay. So how does UEFI talk to hardware without a driver in the way Windows or Linux does? Okay, so standardization here. Hardware manufacturers like RAM or SD must follow strict electrical and logical standards. Okay, so every RAM stick has a tiny chip called SPD, Serial Presence Detect. UEFI speaks a very simple language. I2C. Oh, okay. Now we're talking. Now we're talking. My expertise, right? Okay, so at my job, one of the things that I do very regularly is use I2C to be able to communicate to electrical components and essentially just writing hexadecimal values into those electrical components so that they do what they're supposed to. Like, oh, I want a fan to spin at a certain RPM, something like that, right? So you talk to the fan controller, that fan controller it does its like does the calculations to send the either PWM or like TAC control to be able to spin that fan at a certain RPM, and your life is complete. Okay, but so now so it sends I2C commands to the chip. Awesome. The chip tells it I am 8 gigabytes. I need to run at this many megahertz because the language is standardized. It can talk to any brand. All right. The controllers. They are middle managers of the motherboard. A CPU is great at math, but it's terrible at talking to a USB plug. Okay. The USB controller is a dedicated circuit that handles the messy electrical signaling. Okay, so this is back to those blocks. They're just like essentially FPGAs, but not reprogrammable. Where do they live? Integrated directly on the SoC. Awesome. So built-in class drivers doesn't have a driver for Samsung SSD. It has a generic NVMe class driver. Any SSD that calls itself NVMe must respond to the same set of basic commands: read, write, identify. Okay. It just has I2C commands, like whatever number hexadecimal 2 is going to be identify yourself, and it's going to give back an 8-bit or 16-bit, whatever hexadecimal number, and that's going to be standard. Awesome. Where does the Linux kernel actually live? So the root file system is the body, but the kernel is the brain. So the kernel lives as a file named mvlens or image inside of boot directory of your root partition. Okay. So the loading process, the EFI loader. Okay, so the kernel is actually going to be moved over to the SSD as well then. The EFI loader, the messenger, reads the disk and finds this file. Yep. It copies the file from the disk into a specific location in system RAM. Okay, within my RAM. It also loads a file called this, we saw it, initial RAM disk, a tiny temporary file that contains just enough drivers to find the real SSD. Okay. So EFI loader tells the CPU, stop running my code and start running code at this specific address in RAM. And now that's when the operating system actually takes over. Okay, okay. The handover. The kernel wakes up in RAM, takes over the hardware, and finally mounts the root file system to access. Okay. So, this command is the mover. It ensures every attribute of your OS is preserved. Okay, so archive, the super flag. It preserves permissions, ownerships, and timestamps. X. One file system. Critical. Okay. This tells rsync, don't follow the portal. It stops rsync from trying to copy the SD or the SSD onto itself when it hits. Okay, so this avoids any recursion. Okay. Hard links. So preserve hard links. Multiple names for the same physical data. Okay. A is ACLs. Preserve access control lists. Okay. Now W, whole file, copy the whole file instead of looking for changes. Okay. Extended attributes preserves special Linux metadata like security labels, numeric IDs. So don't map names. Use the raw user ID. This ensures Timothy on the SD card is still the owner of the SSD. Okay. So this shows you a nice overall progress bar. Okay. So this is location independent, as the source here doesn't matter. Okay. I think I am finally ready to start my migration, comma. Please give out the full steps which I need to do in order to complete this task, period. Let's go. All right. So preparation, creating the blueprint. Okay. Formatting, build the warehouse. Yep. Migration, the grand transfer, the switch, telling the manager where the new home is. All right, so what I'm going to do is I'm going to read through all of this, and then we're going to go through it. So phase 1, the blueprint. We need to define a partition on the SSD. We will use fdisk to create the partition table, okay? So we open this partitioner. So this is just a tool, an executable, and I give this target, right? And this tool does the task. It is a partitioner, so that's what its task is. And let me just do like lsblk, because technically the one above was for yesterday's stuff. And then I also can do this df, what was the df minus h, I think it was. df minus h, yeah. So let's just do that. There we go. So this is before, and awesome. Now I think this one, I can SSH into this as well. Judson, there we go. Okay. So now inside of fdisk, perform the following keystrokes. So we are going to G to create a new partition table, okay? We are going to create a new partition, okay? For partition number, so default 1, first sector, okay? Now enter for last sector, so the whole 1 terabyte. So we're going to do enter, so partition number starting at the first sector, ending at the last sector, and then we are going to press W, write, and change the whole disk. Okay, so at that point we have now partitioned it. Okay, so now we need to create the exit4 file system on the new partition. So now we are going to do this make file system exit4 on that partition that we just created. Okay. So this may take minutes as it initializes the inodes and journals. Oh, there we go. There we go. That's what I was looking for, actually. So, okay. Inodes, JOUR, journal. That is what we were discussing. Okay. Where are you? Where'd you go? Where'd you go? That. Remember when I said I hate losing knowledge? That's what I was referring to. I remember it because it was the steps, right? Okay. Well, this is the one where it's talking about Judson hack. So this is after. Where did it give me the like step one? I remember it talking about journals and all of that. Okay. Well, all right, never mind. I don't know, but we'll keep that and we'll just ask follow-up questions later. Okay, so let's keep going through this. All right, so the grand transfer, because my plan is hopefully I'm able to get everything successfully swapped over. Then once I do that, then it's time for me to go in and investigate what I did and make sure that I understand it. And then we can start developing confidently because we're like, okay, we got it and now let's go. Right? So the grand transfer. So now we create a portal and move the data. So we do this we create a directory. Actually, this is make directory. Oh no, but it's make directory, and we are doing an absolute path. Okay. Now we are mounting from there to there. Okay. So then we're doing the rsync. So this is the most crucial step. It will copy everything from your SD card to the SSD. Take about 10 to 20 minutes. You'll see a progress bar. Okay. So now the handover. All right, so we need to tell the kernel to use the SSD's UID instead of the SD cards. Tell the kernel to use the, okay, yes. So find the UID of your SSD partition here. Copy. So we're getting the UID of that particular partition. That makes sense. It's going to be some long string, some long GUID, right? Edit the boot configuration. We are going to the edit file on the SSD, which is currently mounted there. Okay, yeah. And then we can just use like nano or vim to edit it. Okay. Change it to be that UID. Okay, save and exit. Unmount the Oh, okay. Unmount the SSD safely. So then we unmount, reboot the system. Okay. Let's start. Let's do it. All right. So let's all right. Let's start doing it. And now I am going to actually move this over kind of like this. And I'm going to get this with a little bit more room here, right? That way we can see it a little bit better. And now come back up here. And we're going to start partitioning. All right, so sudo nf disk device. Let me actually ls dev, and we should see this NVMe in one, right? Do we see, where's in? Here. Okay. So this is in my device folder, right? Okay, and we also see those blocks. We see our loops. We see I2C. Okay, interesting. All right. So now let's sudo fdisk dev, then nv. There we go. Jetson. Okay, command. We are going to do G. Okay. G. Enter. Created a new GPT disk label here. Okay. New command is in. Enter. Partition number here. Now default is 1. Yes. First sector here. Yes. Now the whole terabyte. Last sector. The end. Enter. Create a new partition. Created a new partition here. Command W to quit. Good. Okay. So now I want to copy and paste this, right? Copy. Here is the output of my fdisk command. Let's go through it and analyze it so I can understand more of the concepts and make sure that I'm connecting everything in my head correctly, period. Okay, paste that into there. There we go. So now, next step, formatting the warehouse. So at this point, I'm going to run the lsblk, and I'm guessing that I'm going to see NVMe, and then I'm going to see NVMe, whatever it in one or something, but then P0, lsblk. There it is. There it is, right there. Oh, that's so cool. Okay. Now, we create the exit file system on that new partition. So now what I'm going to do is I'm going to come here and I'm going to say sudo make file system .ext4, okay, on this device, okay, and now this particular partition. So okay, so NVIDIA GPU, all of those, okay, NVMe, right, and now there should just be this. I was expecting these two, but there's multiple, I guess. NVMe, okay, 0 in 1 P, and then I want 1. Okay, so I did that correctly. And it says that it should take a few minutes. Go. Okay. That did not take a few minutes. Okay. So now 2 is going to be here is the results of my make file system, colon. Okay. And now for this one, I'm going to say, I remember in some of my previous messages, you were mentioning about things such as can you tell me what these things are and what is happening? Question mark. Okay. So now we do this. Now it's time for the grand migration. Okay, so we create it. Now we create a portal and move my data there. So how do I check that? That's going to be the next question. So I think we're on 3, right? Yeah. Okay, so let's go to 3, and I'm going to say, now that I ran my make file system as exit4, comma, how can I check this particular partition and see that it has actually changed to exit4, question mark. Okay. But we are going to investigate this in question 2 of the upcoming, yeah. All right, so now we're going to create a new directory. Okay, so as of right now, I want to ls here. I want to see what's in here. So bin dev, all right. I have mount. Okay, so I want to ls, come on, mount. And nothing is in mount as of right now. Okay, great. So now I want to do sudo make directory in mount. There we go. And I want new underscore SSD. Okay, there we go. And now I should be able to do this and see that I created a new directory. Okay, now I want to do sudo mount. Now I am going to get this device, right, in VME 0N1P, make sure I got it correct, okay. And now I want it to this MNT new here, okay. SSD, like this. Okay, so now we are going to mount it, okay. Go, okay. Next step. And I am going to copy and paste this because I do not want to get the wrong, oh, I missed one flag or something like this, okay? Paste this in. So what are we doing here? Rsync, we are going to come in here and we are going to do all of those flags which we saw, right? Okay, numeric IDs, progress, and we are taking our current file system and putting it all into that portal. Okay. Go. All right. So there we are. And we will see how long that takes. So hopefully if I go like this, woo! What's happening? Okay, there we go. All right, so now we can see everything. All right, so that's going to take a little while. Maybe not, actually. We're already at 72%, so 90. Okay. So, oh, there's a lot of stuff going on right there. That's pretty cool, huh? All right, okay, it's restarted back at, it wasn't up to 100 and then you're done. It was, okay, so now, while that's doing its thing, we need to tell the kernel, so after that, we need to tell the kernel to use the SSD's UID. Okay. Let me, seeing if it was raining. Take a sip of water, or coffee, I mean. Okay. We need to tell the kernel to use, so we're going to talk to the kernel and tell it to use the SSD's unique identifier instead of the SD cards. Okay, so once that transfers over, I'm going to have my portal and I'm going to be able to go into there And I am first off going to check what is the partition tables, like what is this particular partition's unique identifier. I'm going to get that unique identifier, and then I am going to go into that block storage device itself and say, okay, great, hey, go into that boot configuration, and I'm going to edit you. I am going to look for the boot that currently says boot from partition number 1, which is on the micro SD card. I don't want that anymore. I want to do it from this particular unique identifier partition. Okay, and now that is on my SSD. Okay, and then I exit out. I'm just listening, seeing if I can hear any. Okay, and then unmounting it. So another interesting thing. So we have question 3 right there. Why is it important that I do the unmount command? Question mark. What does that actually do? Question mark. So I know that you can unmount for, like, you know, taking out a USB. But now why are we doing it in this situation? You know, then we reboot and verify if it was successful. Okay. Yeah, all right. So now here, so we're gonna have to come back up and look at phase number 4. Start at phase number 4. Okay. So yeah, I was seeing if we can ask another question about this while it's doing it, make sure that it's successful, but let's just ask these questions, understand what we did so far, and then follow things up. So I'm going to say as of right now, my system is doing the command, and as you said, it is taking a little bit of time, comma. So while this command is doing its things, comma, I want to go over the steps which I just did and understand how everything is operating, comma. Then once my rsync is done, I can continue with the process, period. Okay. So, there we go. Okay, so moving billions of bits from your SD card to the SSD. Let's pull back the curtain on what those commands actually did to your hardware. Okay. Awesome. So inodes, journals, the file system, anatomy. Okay, so when you ran make file system exit4, you weren't just clearing data. You were building a complex organizational system. All right. That requires some coffee. So, inodes. Think of an inode as a library index card. Every single file or folder in your SSD has exactly one inode. The inode does not contain the name of the file. Okay. It contains the metadata. Who owns it, what permissions they are, when the file was created, and most importantly, the physical address on the disk where the data block lives. Interesting. So with inodes, if it contains the metadata and one of the most important fields is the physical address on the disk where the actual data block lives, comma. When we're doing the transfer, now all of a sudden we are no longer going to have the same memory address, comma. Is this correct? Question mark. And how does that operate correctly? Question mark. The other thing is, how is it able to identify the file if it does not even have the name of the file? Question mark. Okay. So now the output shows you created this many inodes. Okay. This means your 1 terabyte SSD can hold a maximum of this many unique files. It can hold this many unique files. Okay, so so it's talking about the one where I am doing I don't think it's the format disk. This one is it's talking about this one first. So it's coming in here, and I kind of wish that I had it up right there, but it is doing its thing. So, and it's long gone. It's long gone. Okay. Although we could technically do it from here, but I'm a little bit hesitant to do that while oh, it finished. Look at that, finished. Okay. So now we're going to say, so it did finish. Now I think, no, I can't do it from the other one because it's way up in Oblivion. It's way up here. And these ran, I don't even know, like 36 million lines. I don't think it's actually 36 million lines, but you know, it's way up there. I want to see, does this actually go down like... All right, so now discarding blocks done, 4K blocks. So here's the number of inodes. So creating file system with 4K blocks and this many inodes, right? Okay. File system, UID here. Okay, super block backup. Okay, so now we're talking about super blocks, allocating group tables done, inode table done, journal. Okay, now, so that was that one, and then the partitioning there. Okay, so created this many unique like inodes. But okay, why creating file system? So let's come here and let's say with this, what are the 4K blocks and why does it just come up with the 61 million inodes? Question mark. Okay. File system UID here. So the unique identifier of the file system itself. Okay, super blocks. What are super blocks? Question mark. And so the file system itself has a unique identifier? Question mark. How and when is this used? Question mark. Okay. All right, so now we have got this, right? And now journal. This is a logbook. Before exit 4 actually writes data to the main disk, it writes a quick note to the journal. I'm about to move file A to folder B. Why? If you accidentally pull power your Jetson while it's writing, the file system could break halfway through. When you reboot, the kernel looks at the journal to see the unfinished task and either finishes it or rolls it back. This prevents your SSD from becoming corrupted. That's actually really cool. That's really cool. I didn't know about that. Because obviously, like, you live by these. So this is something else that I find a little bit like interesting about learning about the world, right? Is you live by these kind of rules of thumb. And one of them is just like, oh, well, if you have a device running, don't just unplug power, right? You don't really know why, but just like it's tribal knowledge that, okay, someone told me and now I just follow it blindly. I don't know why. But then once you start to actually investigate and understand what's actually going on, you start understanding, oh, I see why, because the operating system is writing files, and if you just do like unplug the power, it's going to be in the middle of writing those files, and that's going to be corrupted. But then you learn about journals and like, oh, it's kind of keeps it does a record of, hey, I'm about to do this, and then it starts doing it. But if it doesn't complete, then when you boot up, the kernel can look at the journal and say, ah, they were trying to write this, so I'm actually just going to roll back that transaction, or I'm going to complete the transaction. Okay, so analyzing the F disk. So textbook partition setup. Here's what happened behind the scenes. The changes will remain in memory only. When you type G and N, nothing actually happened to the SD card yet. You were building a dummy map in your Jetson's RAM. Okay. Creating the new DOS disk label, then GPT. Notice that fdisk initially tried to give you a DOS label, old school. By typing G, you overrid it with GPT. This was the right move. GPT is required for modern UFEI booting, right? The code in the SPI that looks for the GPT. Your disk starts at sector 2000. Okay, so why not sector 0? Yeah. That's actually what I was about to ask. I was thinking about a follow-up question, but I also want to know, what does disk mean? But that's okay. What exactly do you mean by disk? Question mark. Are you meaning block storage device? Question mark. Okay. We leave the first 2000 sectors, 1 megabyte, empty to make room for the partition table itself. Haha. And ensure alignment. Modern SSDs perform much faster when partitions start on a 4K boundary. Okay. I/O control and syncing. When you typed F, or when I typed W for write, fdisk sent a system call, I/O control, to Linux kernel saying, hey, stop what you're doing and look at the new map for here. Okay. So if you want to see the before and after proof, there are two great ways to check that. So I can do ls blk minus f. Okay, we'll do that a little bit later. I do want to, copy and paste this. And I want to say number 4. Here is a very small section of my rsync command, comma. There are thousands and thousands and thousands of lines which occurred, comma, but I want to know what each of the lines is actually doing, comma, is it saying one line is responsible for a single file success, or is it just updating at random time intervals, question mark? And what can you gain from this data that I show you, question mark? Like that, there we go. Now we can do the F. So ls blk minus f, right? Oh, that is ugly. Okay, but anyways, we have here what we're looking for, and it is exit 4, and it is here. Okay, cool. All right. So here, the importance of unmount. We can't just unplug or reboot. Why can't we just, okay, so the writing cache, Linux is very lazy for the sake of speed. When you copy files, the kernel often says, I'll put these in RAM for now and write them to the actual SSD when I have a spare millisecond. Okay, so so the idea is it's not fully finished writing to the SSD because it's keeping the memory in RAM and doing, it's a, like, oh, I'm done, but I'm not actually done kind of thing. And it will just find time to put that in. So the unmount command, this tells the kernel, stop, no more laziness, flush every single bit from RAM cache into the physical SSD, and close the journal. Okay. So the portal is open. So before, the portal is open, files are flowing, and some might still be sitting in RAM. After, the portal is safely locked, the kernel guarantees that the data on the SSD is consistent, the inodes and the actual data match perfectly. Okay, so the current status, since you're copying roughly 35 gigabytes of data from a relatively slow SD card to a fast SSD, it's normal for this to take a bit. Okay, once it finishes, you will see your command prompt again, yes. Your next immediate step after here, you will need to capture the UID of the SSD and perform the switch. Okay, yep, so that's our next step. We're going to go back up here, and I think we were on like step 4 or something. Phase 4, yep, okay. So let's start doing that. What is our number here? So we were on 5. Okay. Number 5. Okay, so now what we're going to do is we are going to find the unique identifier of the partition which we just created. ls blk no and then uuid on dev nvme in1 p1, right? There we go. There it is. Okay, cool. So now we are going to copy and paste this. So copy U, and now we are going to need to go into our SSD. Okay. And the portal is still open right now. We have not unmounted. We're going to go into there. We're going to find the boot configuration. We are going to use Vim to edit it and say your root is now this partition table, or this partition identifier. Okay. All right, so now I am going to do sudo so that we can change it, and then vim. Now we are going to do mount our new SSD, right? Now we are going to look for exit. Oh, right, boot, okay. Good, okay. Boot, now exit, good. Oh, and there's EFI, okay, interesting. Exit Linux, and now we want to operate on, let me just see, okay, good. Enter. Jetson. Okay. Now we want to go into insert mode, right? Oh, how do I paste in Vim? Okay. Yuck. Okay. I don't see anything that says. Okay. Look for the line that starts with append. Okay. Here. So I see it right there, but I don't know. I do not know how to copy and paste in Vim. Okay, so we are actually going to quit out of this. So I am going to do cat and then all of this. Okay, like that. There we go. And I am going to put this here. Like this. I was able to find the line in that particular configuration file, comma, but I don't know how to copy and paste in, did I use VI or Vim? In Vim, okay. I don't know how to copy and paste in Vim. Okay. So now, once we do that, the next step is going to be unmounting and then rebooting. So that's the only thing that we need to do left. Okay. So, all right. So inodes, I feel like we need to investigate inodes, possibly after this though. Okay, let's actually, okay, so let's try to do this. Okay, so since you're using Vim, let's get you through the edit. It's a modular editor, which means keys do different things depending on what mode you're in. Okay, so follow these keystrokes exactly. So we do the Vim into it, right? Move your cursor using the arrow keys to this, okay? Part. Okay. Delete the old part. Put the cursor on the M of MMC, okay? And press D key followed by the W keyword repeatedly until the old path is gone, okay? Then enter insert mode, okay. And you'll see insert at the bottom, yes. Type the new path, oh, yuck. Double check the string. It must match. Yuck. Yuck, yuck, yuck. That's pretty gross, isn't it? That is pretty gross. Okay, fine. We just need to copy there's no copy and paste? Fine. I'm gonna do this, make sure we have the right 7.4, awesome. Okay, so fine. We'll just do this, and we will go into insert mode, and we are going to just delete this. Fine. Now it's telling me to do it in a slightly different way. I'm kind of curious about how it's saying to do it. But anyways, this is before we get into like so it wants me to do it like, and if we mess things up, we'll just like not write. So on the M and press the D. Okay, so D followed by W. So come here, D followed by W. Interesting. D and W. Okay. Alright, anyways, I think it should be kind of like this, right? I don't know if that's correct. So it is going to be root is equal to UUID equals, and now that long thing. Okay. Now we're going to say 3, 9, 1, 5, 1, A, 1, 4, C, 2, B, 1, 4, 5, AE, 9, E, 4E, 7, 4, 0, B, 0, 7, 7, 9, F, 6, 7, 4. Okay. Now we want to save it, okay? Right quit. Okay. So now I want to run this command, right? And then I want to run this command. And we should see that it is now updated with this. And now I want to make sure that I did that correctly by sending that to AI. AI is very good at checking things. Did I do this correctly? Question mark. Okay. So safety check. Before you reboot, run this command to make sure you didn't actually delete something else. Okay, so yeah. That's actually what I already did. Okay. So we need to come back up here to investigate these inodes and all the other stuff, but later. Right now, let's just try to get this. Okay. So did I do this correctly, right? Okay. Oh, it says wait, stop right there. It will cause a kernel panic, yeah. Because the ID won't match the disk. In your cat output versus your LSBLK here, type a 7 where there should be a 4. Okay. If the kernel looks for this and can't find the disk ID, it will stop booting and leave you in a scary looking text prompt. Okay. Okay, so let's come back here, right? We're gonna do this, And now, apparently, I have made a big mistake, which is... Okay, so 9E 4E. 9E 4E, and then I did 770, okay? But it should not be that. It should be the other one. Okay, so 740, Okay, so let me just hold on. 3915 1A 14-C2B1 45AE 9E4E, okay, dash 740 B0 779 F674. Okay. So now, right quit. Okay. So now I'm going to do the same thing here, here. No, that's not what I wanted. Quit. Okay. Come on. This one, and then the cat. Come on. Cat. Here we go. Okay, make sure that I did it correctly. So then understand, what is this saying? Understand root pivot. Once you fix that, here's exactly what's going on when you hit reboot. Stage number 1. Okay, the Jetson will start, will still read the EFI partition on the SD card. Stage 2, the messenger. It will start the bootloader, which reads my file that I just did, right? The bootloader sees this, okay? The kernel says, I'm going to ignore the SD card for now. I'm going to look at the PCIe bus to find the SSD with that ID and pivot my entire existence onto that drive. Okay. Then we unmount, or sync and unmount. Okay. Then we do the moment of truth. How does it look now? Question mark. Is everything correct? Question mark. And now here, safety net. Because we've only edited the file on the SSD card, your original SD card is a perfect backup. If for some reason the NVMe driver doesn't load, the UUID handshake fails, the Jetson, the one on the SPI is smart enough to realize it can't find the root and will often drop you into a maintenance shell. If that happens, you haven't broken anything. We would just need to re-examine the boot parameters. Okay, good. So now, what we're going to do, we're going to try to finish this. Then we're going to go back up and try to investigate. Okay. So, SY indicate. Okay, it already synced. So, now we are going to do sudo u mount this m, yes, go. Okay, there we go. The big one, that's right, here we go. Sudo reboot. Okay. Okay. So it's rebooting, and I should hear a pop on this thing. It always scares me. Okay. So while that's happening, it's spinning its fans. Okay, so then we do this. So now let's kind of go, while it's doing that, let's assume that it worked correctly, and we'll investigate that. we need to come back up to the inodes. Okay. Ready to back up? See the green light? Okay. So let's SSH into it. See, okay, good. Jetson, good. Okay, now we can do that. What did it want me to do? So we do df minus h here, and we want to see that large thing. No. Nope, it did not work. Okay. So, okay, it didn't work. It looks like it did not work, period. Okay, well, as of right now, we can't go and do all of these. We need to troubleshoot. Darn. Because I really wanted to go and start looking at these, and because those are super important and a lot of good learning to do. Okay. So, anyways. It's very common. First try. You're still on this partition, yes. The reason it didn't work is likely because the sign on the door analogy we used earlier, we changed this on the SSD, but as you recall, the system started looking at the SD card, yeah? If the SD card's own configuration says, look at the SD card, yeah, that's what I was saying. The problem, we edited the wrong messenger. That's what I was saying. When the Jetson boots, it reads boot exit. Exactly. That's why I was so confused. I was like, why are we editing the one on the SSD? Okay. File from the active boot devices. You moved all your furniture over to the SSD. See, by the way, back to the thing of if you were just following the commands, this would have completely thrown me off. I would have been like, I'm so lost. I have no idea how to recover. But now it's like, yeah, I was confused about why we were doing that way. And now it seems like, okay, yeah, like I'm not lost. See, so it really is very beneficial to take the time up front to understand what you're doing first. Okay. But the sign at the old house is still there. The solution. We edit the SD card configuration boot. Okay, so we need to tell the SD card to hand over control to the SSD. So mount the SD card, or the SSD, again, so we can grab the UID if you didn't save it. We did save it. Open the SD card's boot configuration. Notice we are not looking at mount. Okay. Yes. Perform the exact same edit here. Save. Now both signs of the SD card are on. The one on the SD card and the SSD both point to the SSD. This ensures that no matter which one the bootloader looks at first, it ends up on the SSD. Okay. Right, so on the Jetson Orin, the UEFI finds the SSD card. Okay. And yeah, I am still filming. Okay, so I always have to go and check, like, am I still filming? Because sometimes if my MacBook runs out of memory, it just, like, turns off the video. So I need to make sure that I'm still recording. I don't want to just be talking into nothing. All right, so why does the SD card still matter? Okay. The UEFI finds the SD card's EFI partition first. Yes. That EFI partition launches a small program here on the same physical device it started on by changing the file. I know you started on the SD, but I want to go to here. Okay, so it makes sense, right? Now, what we need to do is edit that file on our own thing. Okay. So I'm guessing that it's still going to be the same one here. Let me ensure that. So Jetson, right? And it should be the exact same. I'm like 90% sure that it's going to be the same thing. If it's not the same, good. I have a major misunderstanding in my conception. Okay, because that should be static. It's the exact same thing. Okay. So 74B. Yep, there it is. Okay, cool. So now what I want to do is I want to come in here, and I'm on my Jetson. Right now I'm on the SD card, right? And I need to find my own boot on the SD card, edit the configuration such that it points to that location or to that partition. The EFI partition, right? This partition number 1. No, not the EFI partition, sorry. The root file system partition. Okay. So it is going to be here, right? So now I'm going to do the same thing. Sudo vim on boot, okay, exit Linux configuration, okay, Jetson, okay. Now we're going to do insert mode here, and we're going to change this one out and say, all right, you are not what we are looking for anymore. We are looking for UUID, right? UUID is equal to this one. So let's see if we can do it without making a mistake. 3915.1A14 dash C 2B1 dash 45AE dash 9E4E, right? 9E4E dash, here we go, 740B 077 9 F6 74. Okay. Here, right quit. Okay. Now we're going to do this. And then we are going to cat our boot. Exit Linux. Okay. We're going to come here and we're going to copy and paste and make sure that we copied over everything correctly. Now I'm going to say, does everything look correct? Question mark. Paste that in and go. Looks perfect. Okay. So now we can do sync. By the way, I didn't unmount. Or I didn't mount. I just realized that. Sudo mount. Oh, that's in case we needed to get it. But we did. Whatever. I don't... Yeah, because we're not writing any data to it. Okay, so... Okay, come on. This shouldn't... It should already... Yeah, it's already done. Okay. Sudo reboot. Go. Okay. I am a little bit nervous about it. Little. Okay, so it's doing its reboot. Let's see if we are able to SSH into it yet. If it's going to time out. All right, so it looks like it has not come up yet. I see it still doing its thing. Okay, there we go. Jetson. Okay. DF. Was it minus H, like that? Was that the command? Yeah, df minus H, and here. Whew, come on. We got it. We got it. Look at that. Look at that. There it is. Success. Let's go. Let's go. Oh my. We got it. Look at this. Here we are, and we transferred all the files, and we understood every single step along the way. And now I understand exactly what is going on, where my files are located, physically on the actual device. It's no longer on the SD card, it's on the SSD. We transferred all the files over there. We changed the boot partition that we are for the file system. And I know what that means. I know what the partitions are. I know what the order of booting operation is. We understand. Oh my goodness, today was good. It was a good day. All right, but we are not actually done yet because I want to go and investigate all of those like inodes and stuff like that, right? We still have a little bit more that we need to investigate. So let's do that. I think I'm gonna be right back. And yeah, then we're going to start. So hold up a second. I'm going to be right back. So. Oh. Good, I'm still making a YouTube video. All right, there we go. So I am back. Let's start. Let's keep going. Okay, so I am going to come here and we are going to want the inodes, right? Yeah. Okay, so now let's read through this. Let's do follow-up questions, and let's just say I was able to. We were able to get it successfully. Thank you. Okay. So now I can show this. Okay, awesome. Okay, so now follow-up question number 1, and then we will just kind of go through this and try to get as much understanding and knowledge as possible. Okay, so inodes. This is one of the most confusing parts of Linux. But once it clicks, you'll see why it's so powerful. So, awesome. The name. So in Linux, a file name is actually not part of the file itself. It lives in a directory entry. Okay. A directory is just a special file that contains a list of name, inode, number pair. Okay. So the name and then an inode. And we are investigating what an inode is right now. Let's have another sip of coffee. Hold up. I'm done with that one. Apparently I'm done with this one. And we only have a little bit more water left, so. Alright. Anyways, alright, so make sure we're still recording. Okay, cool. In Linux, a file name is, I wonder how long I can keep recording and then just like, yeah, I wonder how much I can keep doing this, until my like MacBook is like, no, and just the video ends. Alright, so the identity. When you move a new disk, rsync creates a new inode. On the SSD. It doesn't matter that the physical address changes. Okay? Because the new directory entry on the SSD will point to the new inode number, which in turn points to the new physical address. Okay? So if you move to a new house, your social security number, the inode, okay, so inode is like a social security number, stays the same, but the GPS coordinates change, the physical address. So as long as the post office registry directory entry knows your Can we go over what we just did so that I can really understand all of the concepts which are important in becoming a very competent and good embedded Linux engineer, period. Okay. I actually might just say like this, like we just do that and then do the follow-up questions later, but okay, so yeah, I might capture my follow-up questions here and then kind of like do this one by itself so that it will give me an output, a long output, and then I just paste back in my follow-up questions. So actually this one is going to be one right here, and this one is not going to be a number anymore, because then I'm just going to copy and paste this part. Okay, so So what is actually an inode? It's just the social security, right? So it is a number which identifies. So it created all of these inodes. Unique files. So this many social security numbers. Okay. And this was part of the exit 4, right? Okay. So now I'm trying to understand more about what actually occurred when I did the, and then make fs.ext4. Okay? When I did this, you are mentioning that what is happening is I'm actually building a complex organizational system, period. So this indicates to me that each of those different file system anatomies, such as exit4, FAT32, etc., are different ways of organizing data, period. Now, within the exit4 standard of organizing data, there are things which are called, and then inodes. Okay. So inode as a library card. Every single file or folder on your SSD has exactly one inode. Okay, so every single file or folder has an inode. Okay. The inode does not contain the name of the file itself. It contains, what does inode contain? The metadata. Okay. So, follow-up question number 2. If the inode is just a social security number, so like a unique identifier, how does it contain metadata such as permissions, creation date, and the physical address? Question mark. Number 3. When I did the mkfs.ext4 command and it automatically created 61 million inodes, why did it not just automatically create one inode every single time I create a new file? Question mark. So at that point, wouldn't it be almost 0 inodes? And then as I create new files, it will create new inodes? Question mark. Okay. So now the logbook, this journal. So we kind of understand this. That makes sense. Before actually writes data. All right, so fdisk. Created a new. Okay, kind of have that. Disk ID here. Okay. So now I'm going to just copy and paste this. So copy you, right? And delete you. And now we just do that. Okay. There we go. All right. Yeah. Free space. Just in development. You've successfully moved from a slow, unreliable SD card to a higher performance NVMe architecture. All right. So, to become a top-tier embedded Linux engineer, you need to understand that you didn't just move files, you manipulated the boot chain. Yes. Here are the core pillars of what you just accomplished. Okay, so now, by the way, I can do that so that we don't forget about this. So question number 4. Let me take some water. So, the separation of boot and root. In embedded Linux, we often separate where the system starts from where the system lives. Okay. System starts from where the system. Yes, good. Okay. The SD card, the boot messenger. Yes. On your Orin Nano, the SD card still holds the ESP, so the EFI system partition, right? So now if actually, that's an interesting question. What if I did ls blk? What am I going to see? So I was right about this, right? And that's what I was saying. So now, but I still do see all of the block storage devices, including, and notice that it's not there anymore, but including this one, okay, which is still block or partition 10 of my SSD. Okay. This is because the hardware is hard-coded to look there first. Okay? Awesome. And this is where the executable lives for the EFI, which is trained to, I remember we went through everything. The UEFI will go and look at, it will initialize all of the hardware. It will go and look at all of the storage devices that it finds. It will go then in those storage devices, it checks the GPT of each storage block, right? Like this entire thing. And then it searches for this type of partition. If there's multiple of this type of partition, it selects the first one in its boot sequence. From that, it executes this file or this executable, then the UEFI is done. It's over. Now it's here on this executable. This executable will go and it tries to find the root file system. Now that root file system is going to be on, right, the boot configuration, which we just changed. And then we said, hey, where is our root file system? That's right. It is now at the unique identifier, which is here, okay? And now the executable says, okay, great, I need that unique identifier. It then goes, searches, and says, aha, I found the partition. Great, that's going to be my root. There it is, and it boots. There we go. All right, so this is where your actual OS lives. Awesome. You learn that the kernel can be loaded from one device, but told to pivot to an entire existence, or told to pivot its entire existence to another device via root parameter. Yes. Okay. Block device abstraction. You interacted with the Linux virtual file system layer. Okay. You saw that dev NVMe 0 and 1, the raw device, the building. Yes. And before we formatted anything, partitioned anything, any of that, right? I saw this is the logical partition, the room, yeah. So a block device is just a sequence of sectors. Sectors is 512 bytes. To make it a Linux system, you must apply a partition table. So, and that's going to be at the beginning sectors. So sector 0 to sector like I think 2000 or something like that. And that's going to be the partition table. And that's going to say, we didn't even really investigate what's in a partition table, but this partition table is going to say the different partitions where it starts and stops, right? Where the partitions of that block start and stop. Okay. To define the boundaries of a file system here, exit 4. To define the organization. Let me reread that. And I am out of water. I'm out of everything. I'm out of water, I'm out of coffee, and I am out of coffee again. So, all right. So a block device, yes, is just a sequence of sectors. It's just a sequence of sectors. Yep. To make it a Linux system, because as of right now, it's just a bunch of sectors. We need to give it a partition table to define boundaries. The boundaries, okay? So we give it a partition table, and then we also give it a file system, so like the organization. In this case, it was exit 4, to define how the block is going to be kind of like, is it going to be a tree, or is it going to be a... Actually, that's kind of a good way to ask. So is one way for me to think about how these different file systems are operating is to think about different file systems as different data structures, question mark. So for example, when I'm doing leak code, comma, sometimes I am doing a binary tree, comma, sometimes it is a directed acyclic graph, other times it is a matrix, comma. So when I am saying that I am turning this partition into an exit 4, I can think about, I am saying that all of the data which lives within this partition is going to be organized in such a way that follows a particular data structure, comma, kind of like a tree, question mark. Something like that. All right, so metadata and persistence. So rsync and sync. So when you used rsync with those specific flags, this one, you were preserving metadata, right? If you had just used copy, you would have lost permissions, okay? Oh, the other thing that I want to ask is now, question number 5 is, now with my updated understanding and knowledge, comma, can we go back and investigate why I might have been unsuccessful when I was using the Linux dd command, question mark. All right. So, rsync, if you had just used copy, you would have lost permissions. Okay. Yeah, so if I just copied things over, all the files, copied them over, the system wouldn't boot because root user wouldn't own the critical system files anymore. Okay? Engineering takeaway. In Linux, a file is more than its data. It is permission, owner, and inodes. Okay, so now we are getting back into the permissions and all of this. So I'm going to say question number 6 is, can you show me exactly what would happen and what would break regarding permissions, comma, owner, comma, and inodes in this situation, question mark. Okay. So, the UUID handshake, you learned why we don't simply use names like dev SDA, right? So we use the unique identifier for that particular partition, and we don't give like the device that we were trying to say. Yeah. If you plugged in a USB, the SSD might suddenly become SDB1, yeah, obviously. And then crash, yeah. Okay. By using UID, you ensure that the kernel looks for the unique mathematical fingerprint of the partition, making your boot process hardware agnostic and robust. Awesome. All right, the configuration cycle. You experienced the most common gotcha in embedded Linux, writing to the wrong configuration. Now this one is kind of like, and we can, right? I said it in the video. That's why I was so confused, and I was talking about, well, hold on, if I am a USB thing, I can just write to my own boot configuration, and then why would the U or so sorry, why would this executable randomly look into the portal for this USB, right? Come in here, find this, the boot folder inside of like root boot, whatever, exit linux.config. And inside of that, in the USB, then boot. That one. Instead of the SD card, which is whatever, like right up here, right? Like the here, then boot, then Linux, exit. So if there's two, like that didn't make any sense. But yeah, so I was confused about that when we were doing it. I was like, this doesn't feel right. All right, so you realize that the active bootloader is the one that determines the rules. Okay, active bootloader. Even though you had a perfect SSD, the manager, meaning the SD card's bootloader. Okay, so that's the bootloader, right? That configuration file, okay, was the one handling the instructions. Engineering takeaway: always trace the source of truth. Always trace the source of truth, yeah. To change how a system boots, you must find the very first piece of software that reads a configuration file. Okay. So, why do we keep the SD card? We kind of already know this because it has the EFI executable. Even though you are on the SSD, and why do we not just put this over on the SSD? It's because the UEFI looks for the SD card EFI and boots from that, right? But it's okay because this is just on boot up, and we just do this operation once, and now everything, all of our operations are here on this NVMe, which means the kernel, all of my files, all of my models. And so now everything is going to be really fast because we just boot from here, but then when we're actually operating, this is where we're doing the operations. And so we can swap from SSD into RAM a lot faster, which was one of the problems. Number two, the second problem was with the micro SD card. If we do too many read writes, it wears out the card. But now the SSD is much more robust. So we fix a lot of those problems. Okay. So now, even though the SSD, you're on SSD, you don't take the SD card out. On the Jetson Nano, the SPI flash, the UEFI, expects to find EFI partition on the SD card and start the UEFI environment. If you remove the SD card, the handshake fails before you even start. All right, now that you have this step, your AI will be running significantly faster. Okay. Move doc, no. We're going to do this and then probably end the video out. That's what I'm thinking. And then obviously the next steps after, so we've completed this successfully. And then the next step is now I need to go in and we're going to continue developing to try to get the speaker microphone working. We're able to use my voice to talk to it, right, and transcribe that into words. But now what we need to do is be able to plug that into an AI model. We also need to be able to use, I think it was suggesting Piper, to go from text back into speech, and so I can hear the response. So we still have a lot of work on the AI side of things to do, but now we are in a much better position. Okay, but anyways, let's do this, and then we can do like next steps, the outro. Okay, so file system as data structures. So you hit the head nail on, you hit the head on the nail. Okay, you hit the nail on the head. I can tell that I'm starting to get a little bit like need to take a little bit of a break. All right. Let's power through it. We got it. Okay. Turning into a partition. Making sure that I'm still recording. Okay, good. Turning a partition into exit 4 is precisely like choosing a data structure in LeetCode. The data structure, exit 4, is essentially a tree-based structure, yeah. Specifically using H trees for directories and extents for data blocks. Okay. The standard, just like a binary search tree has a rule, left is smaller, right is larger, yep. The exit 4 standard has a rule. Okay. Exit 4 standard has a rule. Every file must have an inode. Every directory must be a list pointing to these inodes. Ah, that's a directory. It is a list of inodes. Ah, okay. See, I love connecting and putting puzzles together, and then you get a more holistic understanding of the entire system. I wasn't even thinking about understanding directories when I was trying to investigate how to swap over my micro SD over to SSD. But now we have a much better understanding of Linux in general, the boot process, how the files are organized, all of this. Like, I love being able to like keep putting the puzzle pieces together, and then you connect one like group of concepts up to another group of concepts, and now like it just fits into pieces, and you're just like, oh, that's awesome. All right. So the difference, FAT32 is a much simpler structure, more like a linked list. Ah, okay. It's easy to read but slow for large disk and lacks the security fields that Linux requires to run. Okay. So it's slower, but that's fine for this, right? This one is FAT32. It's slower. It doesn't have the security features. That's fine though, because this is just the executable that's gonna boot things. Okay, so inodes, more than just a number. I use Social Security as an analogy for its uniqueness. Got it. But technically, an inode is a struct. Okay, a fixed size block of memory of the disk. Okay, when you format the disk, exit 4 carves out a specific area. Okay. When you format the disk, exit 4 carves out a specific area of the disk called inode table. So when I do that for exit 4, I'm also going to be creating a table on the disk. Got it. Good. Each entry in that table is 256 bytes. Okay. inside the 256 bytes, the standard defines specific offsets. So offset for 0 to 2 is permissions. Okay. And this is bytes, I'm assuming, not bits. 4 through 8 is going to be the owner. And then offset here. Yeah, so it shows bytes, but comes up to 100. 256, but 100. Anyways, whatever. The I know number is just the index in a massive array. When the kernel wants to read a file, okay, when the kernel wants to read a file, it says, give me the data for inode number 500, okay? It calculates the memory address, starts the table. Okay, actually, let me just shut this down. So, sudo shut down now. Okay, Jetson. All right, this thing's probably gonna click. Always does that. There we go. See? But anyways, the I know number is just an index. I'm trying to power through this. It's just an index. When the kernel wants to read a file, I want to read a file. Okay, give me the inode, the data for inode number 500. It calculates the memory address. So we go to the start of the table, and then we say 500 plus this, and reads the metadata directly. Okay. So it's fixed sized versus dynamic allocation. So the problem in exif4, the inode table is a physical area on the disk. Okay, now I'm starting to see, okay, fine. If you didn't pre-allocate it, you're filling in the disk with 900 gigabytes of movies. You would have no physical space left on the silicon to write the metadata for a new file. Okay. The solution. This command that we ran reserves about 1 to 2% of the disk space immediately to act as a cabinet for the index cards. Got it. Why is it not 0? That we kind of understand that now, right? Like if you created one by one, the index cards would be scattered all over the disk, and looking up things would be horrifically slow. So we would have fragmentation. By pre-allocating a continuous block of memory for the table, the disk head or the SSD controller, right, that fetches data, can find them instantaneously because it already knows where to look. So why did DD fail? And this is back like 4 months ago when I was working on trying to do something to transfer over a Raspberry Pi image, and I was using DD. And so why did that fail? All right, now that you know about inodes and partition tables, DD's failure makes perfect sense. What DD does, it is a dumb copier. It copies sector 0 to sector 0. Yes. The conflict, if you use DD on a 16 gigabyte SD card onto a 1 terabyte SSD, okay, yeah, you're copying a partition table that says this disk is 16 gigabytes. Okay, yeah. The result, even though you have 1 terabyte of hardware, the data structure, meaning the partition table, you just pasted tells the kernel the disk ends at 16. Yes? The kernel sees end of disk marker in the middle of your SSD and assumes the rest of this doesn't exist or is corrupted. It's like passing size 10 array into a size 100 memory block, but leaving the length variable to 10, okay? And I am kind of rushing through this a little bit because I can feel that my head is like, I'm starting to get tired. Need to take a break, go for a walk, something. Okay, so why copy breaks the OS? So if you had used copy here, so we're copying over what? We are copying over all of the files in my root partition, which used to be here, right? Over into our new partition, which is like the mount, which is going to be in there, right? Instead of rsync, Judson would likely never reach the login screen. So the owner breakage. On your SD card, the file user bin sudo, okay, this executable here must be the owner or must be owned by a root user and have special set UID permission bit, okay? If you use standard copy, the new file on the SSD might be owned by Timothy, the user running the command, okay, not root. When you try to boot, the system tries to run a service, looks at the inode and sees, wait, the critical system file is owned by Timothy, not root. This is a security violation. Then we get a kernel panic. Okay. So, inode and link breakages in Linux. So Linux uses the symbolic links. The copy command often tries to copy the contents of the shortcut rather than the shortcut itself. You would end up with 2 copies of 1 gigabyte file. 2 copies of 1 gigabyte file instead of 1 file and 1 tiny shortcut. You'd run out of space and the paths would be broken. Okay, so going back over kind of the summary of what we learned. All right, make file system. So this defining the data structure, right? Allocating the actual inode. So the file system that's going to be exit4 or FAT32. We did exit4, and so that's the data structure. That's like a tree, right? That's a graph. And so we are creating the table which says where everything lives. And we're pre-allocating that with whatever the 60 million inodes, and then we can create the tree. So mount is mapping the hardware to the software path, right? So we have our physical. This is before we did any of the changes. And changes, I mean, like this is just so when I just put in my SSD and I was running on my SD, I needed to mount my SSD. So what that meant was say, hey, I see this thing here. I see this thing. It was right there. Okay, and I wanted to say, all right, well, I need a portal from my software to be able to actually interact with this actually it was this one right here, this block storage. So I did a mount to a specific folder on my SD card file system. So from the root, and then somewhere in there I did like mount, and then I said, hey, here's a mount which points to this block storage. Once I pointed to the block storage, I said, great, awesome, now I can first off partition it. So we used the whatever partition command, the executable, gave it the target, which is now mounted. So we were able to do that. And then we gave a GPT, so a general partition table, to that partition, to that block storage device, right? Block storage device, this one here. Then we said, okay, great, I'm going to create a single partition. That single partition is going to start at the next available sector, which we just created the GPT. So now the next one is going to be whatever the 2000 sector 2000 48 or something like that. We are going to go all the way to the end, and then there was one other thing which we set for that. So now we have this partition right here, okay, without the, not that, but just like this. So we have this partition, and we say, okay, great, awesome, we have this partition. Okay. Now what we're going to be doing is, now this is just, we just partitioned it. We did not set any type of file structure. So it's still just like a block of memory. So now what we're going to do is we exited out of the partition tool, and then we said, okay, great. Now what we're going to do is I'm going to format it to be exit 4. So then we did that command that says exit 4. And what that does is it created all of those inodes. It created the table that has the location for all of the inodes, and it set things up according to the data structure of exit 4. Great. So now we have this partition, which is part of this block memory, which has been mounted to a portal in my file system, okay? And we have set it up such that it conforms to the exit 4 architecture. Okay, great. Now what do? Now the next step was we decided that, so this is actually going to go and look for where to boot from. It is going to look for the root. Now, previously the root was right here, okay? But we want to change the root to be right there. So how do we do this? All right, so this executable, the executable that lives in here, it is going to look for something which is inside of the configuration boot. So let me show you where that is. So we have, I will do like, let's change directories into, and we want, from here I believe it is just boot. What was that file location? It was, okay, so let's just go into here, right? And now I'm gonna say ls, isn't there a, okay, so let me get my bearings. Temp dev bin user, I thought, okay, hold on. Let me check the exact file location because I remember the command that which we were just doing. Come on. Where are you? This. So /boot. Okay, so I had the right thing, but let me come up here because we're currently on our other one. Why is should be there, I thought. Interesting. So, okay. But it is obviously not ls minus la. Do we see anything that says boot? Grep boot. Can we do that? I don't know. Okay. But, okay, so anyways, there is a file. Maybe I need to investigate again where it actually lives. But there's this configuration file, which is currently living inside of my file system. And my file system on my SD card, okay, so it was living in /boot/exitlinux/exitlinux.config. Now, what I needed to do was I needed to go in and edit this configuration file. And what does this configuration file do? It is what this executable is going to look for. It's going to look for the boot configuration. It's going to go in there. It's going to check, where is my root file system? And now previously the root file system said, hey, you are right here. And then the executable said, great, awesome, let's go, let's load it. So it loaded this as the root file system. Okay, but now I don't want that anymore. I want it to load this as the root file system. So what did I do? I went and I found the unique identifier for this particular partition, and then I just put that in the configuration file up here, and I said, hey, where is my root file? Root equals what? Root equals this partition. And so now when this executable loads up, we are going to say, we're checking here. We see, there is a configuration file that says that I should load this, and it does. Now this is the root file system. It loads that, and then the kernel wakes up, and bam, we have successfully booted and gotten into the SSD. So that's kind of the thing which we accomplished today. It's working. And we also, the most important part is not just that it's working, that we understand it, that we learned an immense amount of knowledge, and we have grown as engineers and been able to get a more holistic understanding of how Linux is operating, how all of these things actually work, and we're going to be able to be more competent and confident in this realm of Linux development. So I will classify today as a very successful day, and hopefully we are going to continue not hopefully, we will. We are going to be continuing in these projects. I'm going to be continuing to post more videos, so if that is interesting, subscribe to this channel. I would love to have you along, and we are going to continue to be learning more concepts. Specifically, what I think I'm going to be doing in the future is, what I want to do with this project is, we have our AI models, and I want to be able to understand how orchestration is working. How am I able to, from Python, be able to invoke tools? How is the LLM actually invoking tools? So I want to be able to speak in to this microphone. I want to be able to transcribe it into words. I want to then be able to take those words, put it into my LLM, have my LLM decide what it wants to do, right? Orchestration. Invoke this tool, invoke that tool, then maybe loop back around, and then finally perform actions. Then give me an output, a friendly output, right? Friendly output. So one output is more of the technical, that's the tool calling. Then the other one is going to be more of the friendly, chatty output, okay? And I wanted to have it both in English and Chinese. And then, so once it gets the output, then I want it to be able to then I will need to be able to take those words, the words which the LLM generated, transcribe them, or actually it would be the opposite of transcribe, but take the words and turn them into like sounds, like audible words. So written words into audible words. And we're going to be using, I think, Piper for that. Now, have that be spoken out from the speaker. So that way I can talk in to the microphone. It does the commands. The LLM works its operations. And then I get a response back. And it says, I have successfully completed this task, and blah, 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 right? And it talks back. And as I just mentioned, I want to be able to speak to it in both English and Chinese. So I want to have it be able to, like, if I speak to it in English, it goes, does everything, responds back in English. If I speak to it in Chinese, it should be able to go and do its thing and then talk back in Chinese. So that's kind of what I want to do. That's where we're heading with this project. If that sounds interesting, subscribe, and we are going to continue to be moving forward. I am having a great time with this project. I am learning a lot, and it's super fun and interesting. So yeah, thank you for watching. My name is Timothy Lee Grant, and I will see you guys in the next video.